Well, good afternoon and welcome back to the Johnson Space Center for today's status briefing on the progress of the STS-107 mission aboard Columbia. With us today to discuss the mission and the scientific research on board are Phil Engeloff, the STS-107 mission operations representative, Dr. John Charles, the STS-107 mission scientist, Dr. Gerard Faith, the principal investigator for the laminar soot processes experiment, and Cindy Hutchins, the principal investigator for the vapor compression distillation experiment. And we'll start off with Phil.
Thanks, Rob. Okay, well, I'm happy to report today again that the orbiter and the crew are all doing very, very well. The crew are staying well on the timeline. They have a pretty high level of activity and they're pressing through their scheduled experiments and operations pretty much right on schedule. They're all in good spirits. Everybody seems to be doing real well. The orbiter also is doing great. We have no significant anomalies to report on the orbiter, no real changes from the report I gave a couple of days ago. And the only thing that we have of any significance to talk about is at this point an annoyance, and we think we're going to be around the corner on that. We have had a cooling problem with the Space Hab cooling system, and it's technically actually a problem with separating out condensed water. The cooling system is cooling okay, but in order to avoid getting a lot of condensed water under the floorboards back there, we've had to back off on some of the cooling to minimize the condensation, and we're in the process of a workaround. The Space Hab has a couple of pieces of rotating equipment that we call rotary separators. For those of you familiar with the orbiter, they're basically the same thing as the humidity separators. At home, in your air conditioner, when you pass the cold Freon through your air conditioner and then blow air over that, any moisture in the air condenses out on the coils, drips off into a pan, and runs down a drain somewhere in your house. In a similar fashion, when we collect condensation on the heat exchangers in the cabin by blowing air over cooling fins, that water collects, but it doesn't run off because there's no gravity. As a result, we draw that off with airflow, and by using a rotating piece of equipment, we centrifugally separate out the water and force that off into a tank and blow the air back out into the cabin. A couple of days ago, we had a problem with one of those rotary separators, number one, in that it was flooding and not pushing the water off into a tank. So we had to shut that rotary separator down and switch to the alternate rotary separator 2, which ran fine, collected the water in the tank. Subsequent to that time, we did have an electrical short which opened 2 of the 3 phases of circuit breakers that were ultimately powering that rotary separator. And since that period of time, we've been operating without the rotary separators working. As a result, we backed off some of the cooling by diverting the airflow so it didn't go over these coils. Since we couldn't make the water go to the tank without the rotary separators, we didn't want the water collecting under the floorboards. We've made a couple of configuration changes on the orbiter to try to compensate for that. Ultimately, the orbiter provides all of the cooling for both vehicles. We have the radiators on the orbiter payload bay doors that radiate the heat to space. There's Freon passing through those, and we have a heat exchanger that basically runs water through the coils, and then we run the Freon past those coils, and we run heat from the cabin into the Freon that goes out and gets radiated into space. So that water that we cool in the orbiter gets pumped back into the Space Hab and provides the chilled water that ultimately is used to cool the cabin air back in the Space Hab. Without the capability of the water separators, we're doing what you might do in your house if you had an upstairs air conditioner and a downstairs air conditioner and one of them wasn't working. We've turned that one off and we're blowing cool air from the orbiter back into the Space Hab. We always have some amount of air exchange between the 2 vehicles, but to compensate for some of the degraded cooling, we've turned the temperature control in the orbiter down, so to speak, to chill that air somewhat more than normally, and then we're flowing that air back into the Space Hab to provide a compensation for the loss of cooling back there. We're in the process of trying to implement a short-term fix, or a quick fix, I should say, by adjusting the amount of cooling water that flows to different parts of the space hab to provide more cooling to some of the equipment racks in order to allow us to keep all of the experiments operating. And even though the air temperatures are a little bit warmer in the hab right now than they would normally be, it's really not a factor for the crew. It's really not even outside their comfort level. And until we told them initially that we saw the temperatures rising, they hadn't even realized that the temperatures were going up in the hab. So we think we have the temperature problem essentially under control. We do have one experiment that was affected by the loss of cooling. We lost one data take on an experiment today. With this fix of adjusting the water flow, we expect to be able to operate that experiment tomorrow, and we don't believe that there's going to be a loss of science by the end of mission. We think we'll have recovered everything. But that's really the only issue that we've got to talk about in terms of orbiter or space hab systems. And as I say, at this point, it doesn't look like it's going to be an impact to science over the duration of the mission. So I guess that's basically all I've got to say. I'll pass it over to Dr. Charles.
Thank you, Phil. The scientists supporting this mission are very happy with the productivity and the results coming out of this mission so far. We're only just getting started, lots of time left. We're going to be hearing from several of the scientists over the course of the rest of the mission during these briefings. Today we have two with us, Dr. Jerry Faith of the Laminar Soot Processes Investigation, and Cindy Hutchins, who'll tell you more about the vapor compression distillation investigation. Before they speak, let me give you a brief synopsis of the rest of the NASA Code U, that is the Office of Biological and Physical Research investigations over the last day or so. Yesterday, one of the fundamental biology investigations, the BRIC payload completed the first of 11 chemical fixations of moss samples. The moss samples are being studied for their sensitivity to environmental factors and specifically their growth patterns in the absence of any environmental factors, in the absence of gravity, in the absence of light, and so forth. The moss samples had been exposed to a directional red light up until one day after launch, and now they're growing without stimulus. We're hoping to see if they duplicate their behavior on STS-107 when they grew in a spiral. All of them uniformly grew in a spiral. The first fixation of moss samples was yesterday. Subsequent samples will be fixated every other day or so for the remainder of the mission, out to day 14 or so. So that experiment is progressing very well. The rodents on board are doing very well in flight. Two other fundamental biology investigations haven't begun yet, but we'll be telling you more about those when they do start. In the area of human life sciences, the so-called medical experiments on board, the payload crew has completed the first go-around, the first 6-day go-around of blood and other body fluid collections as part of an investigation to understand how proteins, how the body's muscles and the body's bone and calcium stores and other parameters change with time and flight. Five blood draws were accomplished on all 4 payload crew members, and 2 tracers were injected in the 4 payload crew members. All 7 crew members are doing daily saliva collections for us to understand how the body's immune system changes in flight. And they're logging with the barcode reader their food and exercise daily activities. So the payload crew will continue with their frozen and their ambient saliva collections. Some of the salivas are collected and frozen, some are just stored in a pouch in a location in the cabin. And the orbiter crew concluded their urine collection today, but the payload crew will continue with that as well over the remainder of the mission. Yesterday, another human life sciences investigation had a slight setback. There's an experiment named Microbial Physiology Flight Experiment, and it's a modification of a commercial piece of hardware. One of the card trays jammed in the reader yesterday, and it took so long to get it unjammed that the specimens on the card tray were considered lost because of exposure to ambient temperature. But there are 6 card trays during the mission to be collected during the mission, and the 5 remaining should give practically all the information required. So the experiment will continue with the incubation and the analysis of subsequent card trays. Our sleep study is continuing with nominal operations. In the area of microgravity sciences, we'll hear from Dr. Faith in just a second about the combustion module experiment to laminar soot processes, but the investigation looking at compaction of simulated soil, mechanics of granular materials, has completed 5 out of 9 runs so far for the mission, 5 out of planned 9 runs, with a 6th run planned for later today. They are on timeline and progressing very well. And the bioreactor, the biotechnology demonstration experiment that is running, you may have seen the rotating vessel on some of the NASA TV earlier today, is going very well. The cells are accumulating and clumping spectacularly. Its growth that seems to far exceed growth that is found in similar cultures on the ground. So we'll be telling you more about that as the mission progresses. The other microgravity science experiments are progressing all normally today as well. So that concludes the brief overview of the basic and applied sciences in the NASA allotment. I'd like to turn it over now to Jerry Faith to tell you about one of those investigations, the laminar soot process investigation. Jerry?
Thank you. Tests carried out by the astronauts on Space Shuttle Columbia over the last 5 days really have provided very valuable results and have exceeded all my dreams for what we could get. In essence, we've been preparing for this flight for 6 years. I sort of feel like a prize fighter that's trained for 6 years and has finally won the bout. I'd like to tell you a little bit about what we've found out and why it's significant. First of all, let's define some properties of soot in flames. Soot really is small carbon particles, and when these carbon particles are hot in a flame, they glow yellow, and that gives the characteristic yellow color that we're all familiar with. When they come out of the flame, they yield up a black plume. That is also a familiar sight when you observe soot-emitting systems. Soot particles are small. They take about 1,000 soot particles to go across the diameter of your hair, for example. Unfortunately, they readily deposit in lungs and during breathing, and that makes them a possible source of health problems. In fact, soot is widely recognized as a bad-smelling and irritating pollutant. In fact, it really causes more deaths, 60,000 a year in the U.S. alone, per year than any other pollutant that we know of. LISP experiment itself involves exploiting several ideas. First of all, typical practical flames, for example, a campfire or something you might see in your fireplace, are turbulent. That means they're very unsteady and they flicker. And they are really little affected by Earth's gravity. So therefore, due to the unsteadiness and the like, studying soot in practical flames is not feasible. In particular, very poor spatial resolution for measurements, and you need lots of measurements to learn anything about soot. Studying soot in a steady, non-turbulent flame in Earth's gravity, like a candle, seems like a very obvious step. But in fact, it turns out to be very misleading in trying to get to the fundamentals, and I think studying candle flames has had a lot to do with our rather slow progress towards studying the production of soot in real flames. On the other hand, if you can observe soot processes in steady, gravity-free, non-turbulent or laminar flames, flames that have smooth surfaces like candles, those kinds of measurements are both feasible and appropriate as model flame systems for practical flames. And that's what our interest in these flames is motivated by. Thus, the objectives of LISP are to observe the properties of gravity-free, soot-containing laminar flames, and to determine whether these flames provide good models of practical, turbulent, soot-containing flames. I believe they have an example of one of our tests, and if that could be run now, I'll give you a better idea of what we're talking about. This is the start of the experiment. This is an igniter wire that comes in as the burner is on the left, and you can see the flame coming out and growing. Now the operator along Ramon gradually increases the velocity of the flow to achieve a fairly large flame, as you see. You could never see a flame like this on Earth, so you're seeing something that no human being has really ever seen before. But you can see it's large and spread out, and it's steady or stationary, and it'll be the same from month to month, and provides an excellent test bed in which to study the properties of soot. To go on, the main findings of the experiments this week are, first of all, the measurements show that soot processes in practical turbulent flames are correctly modeled by these gravity-free flames that I've just shown you. They also clearly provide a large and slow-moving laminar flame that's tractable for the detailed measurements you must make to study soot. Thus, future experience involving gravity-free flames should provide rapid gains in our understanding of this public health problem, the generation of soot in flame environments. In fact, recent work exploiting earlier LSP findings from earlier flights have disclosed ways to eliminate soot in practical turbulent flames entirely, converting them to blue flames or soot-free flames. Upcoming flame experiments on the International Space Station, a series of experiments called SPICE, S-P-I-C-E, will seek to confirm these findings for gravity-free laminar flames. Thank you.
And next we'll ask Cindy Hutchins to tell us something about the vapor compression distillation investigations.
Thank you. Good afternoon. The vapor compression distillation flight experiment, or VCD, has successfully completed 3 days of operation, and we're very happy about that. We've been getting good data downlinked to us, and so far it looks like what we expected to compare the data to the ground data. The vapor compression distillation flight experiment is a similar system to what will be used on the space station to recycle the crew's urine into potable water. So this is very important to get our data to make sure that there are no microgravity issues with that operation. The vapor compression distillation flight experiment takes water, it evaporates it at a low pressure, and then condenses it, and then the clean water is pumped out of our system, and all the salts and other things left in the urine are collected, and then they will be returned to Earth when it's used on the space station. So we feel like this is going to be a great improvement to the space station because the crew and the shuttle will not have to take up so much water. It's going to greatly reduce the amount of water that has to be lifted to the space station, and it will help the crew to have good drinking water.
Okay, thanks, Cindy. And we'll take questions here in Houston. Before going down to the other centers, please state your name and affiliation. We'll start with Mark.
Yes, I have one for Dr. Hutchins and then a couple other questions. The experiment of recycling the water, is there sort of a rough time frame when this technology would mature to the point it could be on the space station? Are you aiming for a certain period of time?
Yes, we are. We're right now developing our hardware. We're building hardware to send up, and it looks like our schedule right now is 2006. Yeah.
And just to follow up on that, is this hardware then that you would use as a prototype on the space station for an advanced spacecraft that would travel in interplanet? I mean, I just wonder where this is really going in a development sense beyond the space station.
Yes, this will definitely be useful for long-term space flight. There are also some ground uses that it could be used in remote areas where you need a very small system. We built our system very compact and very lightweight so that it could be used in space, and this would be very important for longer-term space flight. And I believe that the use on the station will prove that that's going to be a very good use of the hardware.
Okay, thank you. And I had a couple for Phil and Gloff on the humidity separator. Can you kind of lay out what your strategy is in the sense, are you in a position where you need to repair one of the two separators in Space Hab, or would it be possible to sort of manage this problem as you are now throughout the extent of the 16-day mission? And I guess somewhere in both of those questions is for you to gauge, can you make the whole mission if this is a problem you can't fix?
The simple answer is we're optimistic that this little bit of diverting water from one loop to another, or one part of the loop to another part of the loop, will actually get us to a configuration that we could live with for the rest of the flight. That's the simplest way to solve the problem, and that would be our preferred method. To be just a little more elaborate than I was in my original description, the water that comes back into Space Hab from the orbiter cooling provides a couple of different purposes. Indirect cooling in the sense that we blow air over it to chill the air and use that for ambient cabin atmosphere cooling. We also run some of that water over other heat exchangers and then take some of the water that's cooled by those heat exchangers and run those through the payload racks to keep the experiments cool. We're operating in pretty much a stable configuration right now, but some of the payloads that require a higher heat load, like VCD, for example, running in conjunction with all of the other experiments, we really need a little more heat rejection capability. So part of what we're going to do is to try to divert a little bit more of the water to the racks in order to cool the experiment loop so that we can run all of the experiments. And we think we've already got the cabin temperatures under control in a livable condition. So if we can solve the heat rejection for the payloads, we think we can fly the rest of the mission in that configuration. A more aggressive solution would involve trying to repair one of the two water separators. One of them we think flooded, like I say, and we think that might be due to blockage, and we'd have to dry that out and resolve the blockage if that turns out to be the problem. The other one we think was an electrical short. We don't know exactly where that is. We'd have to go in and do some troubleshooting and try to find out where the short was. If that was due to residual water, maybe we can clean that up. But we always prefer not to go in there and try to repower equipment that's had a short on it if we can avoid it. So the first solution is really the preferred option.
Okay. Questions now down at the Kennedy Space Center.
Hi, this is Chris Cry in Florida today. My questions are, I have a couple questions for Cindy. How much energy does this recycler use? It's not just like flushing a toilet, it sounds like.
This is a phase change process, so it is fairly energy intensive. But compared to the amount of water that you would have to lift, it's still a very good solution for recycling, for taking water up to the crew. But it is a more energy intensive process than, say, a filter would be, because it does change the water from liquid to steam and then back to water. So it is a fairly energy intensive operation.
Is this something that could also be adapted for Earth use, say an expedition in Antarctica or something like that?
Yes, I think that would be a very good use for this equipment. The Navy has talked to us about using it on submarines. Any small remote area where you would need clean water could use this system. Ours is fairly expensive because of the materials it's made out of, and we have to get it into a really small area, but it could be enlarged or other materials used that would not be quite as expensive and that could be used here on Earth as well.
And last thing, what are those materials that it's made of, and what are you using to represent urine in the experiment? Because I understand actual urine is not being used.
That's true. We use a lot of titanium in our system because of the corrosive properties and to reduce the weight. We are not using urine in this flight experiment. We are using a water that's chemically treated so that we will be able to compare that to urine and see that it operates the same. We're running ground tests with the same water so that we can compare directly how it operates in space. But it's a water treated with some chemicals to mimic the urine.
This is Marcia Dunn of the Associated Press. Following that up, why aren't you using actual urine? Why not?
Well, to use the crew's urine while we're on orbit, we would not be able to collect enough urine to prove our hardware works well. To fly urine up was going to be a little more difficult because of the safety issues that would come up with having urine that had been stored for quite a while to be flown up. And our experiment did sit for a little while on the ground before it flew up, and we didn't want to take any chances that urine sitting for a while before we flew it would cause us any problems. So we just thought the easiest and safest thing would be to fly the water.
Thank you. And Phil, a couple questions for you. Could you give the range of temperatures you've experienced in the space hab, please, from before when this problem hit until afterward, until now with some of the cooling in place?
Sure. Normally we run the cabin atmosphere temperatures throughout the vehicle at in the range of 72 degrees. The crew has a little bit of adjustment capability for comfort level. After this problem materialized, the Space Hab ambient temperatures peaked at, I believe, about 84 degrees and then started to fall back. After we adjusted the temperatures of some of the loops so that we could flow air across the heat exchanger again without getting condensation, we've managed to get the temperature back down to about 76 degrees just before I came over here for the conference.
Thank you. And I heard Rick Husband reporting last night that it was very cool in the flight deck, comfortable in the mid deck, and of course warm back in the hab. First of all, why would there be such extreme differences in 3 different areas? And if that's the case, wouldn't it be prime territory for a crew member to get sick with a cold up there going through such extreme changes?
Well, I can't really speak to the crew getting a cold. I'm sure there are other factors involved there. The technical reason for the difference in temperatures is that primarily the air exchange between the Space Hab and the orbiter is with mid-deck air. Essentially, we draw in air, run it through the heat exchangers, and send it back to the Space Hab, and then the return air comes down through the tunnel. So you're taking the orbiter air that has just been chilled by the heat exchanger, and some of that comes out in the mid-deck, some of that comes out through the systems into the flight deck, and some of it goes directly into a duct that gets pumped straight back into the Space Hab, where it mixes with what is now warm air back there because of the reduction in cooling. And then for every pound of air, so to speak, that we put back into the Space Hab, a pound of air comes back through the tunnel into the mid-deck. So we're continually mixing warm air back into the mid-deck. Less of that air tends to migrate up to the flight deck. Another part of the problem is the amount of equipment that's running. We've sized the cooling systems and air ducts on the orbiter to account for the large amount of equipment that we might have running during ascent or during various other phases of the mission, like rendezvous, where we have a lot of computers running. But for a mission like this, where we're basically flying in a stable orbit and actually in a fairly powered down configuration, it tends to make the flight deck somewhat overcooled compared to the mid-deck. So you get 3 zones, so to speak. A very cool mid-deck, flight deck, because we have essentially turned the temperature control in the orbiter down, but then we have the warm Space Hab that has some limited cooling, and a pretty comfortable mid-deck because we're mixing that warm Space Hab air with the cooler cabin air from the orbiter.
Thanks. Do you know how cool it got in the flight deck last night?
Unfortunately, the way our temperature sensors work, we pretty much get the mid-deck temperature, and we don't have real good insight, so most of what we get is subjective judgment from the crew of what the temperature is. We do have some little meters, like a voltmeter with a temperature probe that we can take up there, but it varies a little bit from spot to spot, and there's really not a lot of scientific value in doing that. If the crew says it's cool, then it's cool.
Thanks. And what was the one lost science that you mentioned that you'll pick up tomorrow? I wasn't sure which experiment that was, and I'm wondering, I'm still unclear, did you say that you think this solution in place now will be okay, or are you considering or going to put in place one of these actual repairs where you actually get your hands on these separators?
I believe VCD had a data take scheduled for today that they were unable to do because we didn't have the cooling in place. Their next scheduled opportunity is tomorrow, and assuming that this water diversion repair that we're going to do works as we expect it to, they should be able to operate tomorrow, and we should be comfortable in that configuration for the rest of the mission. It shouldn't compromise any of the science, and we should be able to accomplish all of the objectives. We're also hopeful that we will accomplish all of VCD's planned objectives by the end of the mission, either by recovering the run that they missed today or by taking advantage of their other opportunities to collect any data that they might have missed today.
I guess I'm still a little confused. Does this water diversion plan involve taking up the Space Hab floor and actually looking at what might be wrong with these separators?
The separators themselves, essentially we're going to open the floorboards, and there are some manual valves in the system that are used to balance the water flow from one part of the cooling loop to another part of the loop. It's a little hard to describe without a drawing, but it's not as simple as just a water loop going from one place to another. There are warm zones and cold zones and valves that adjust the amount of mixing of warm water with cold water going to this loop and warm water with cold water going to that part of the loop. And basically we're going to get in there and adjust those manual valves just a little at a time to try to keep the balance of temperatures where we want them to, but to increase the amount of cooling that we're getting to the payload experiments without overcooling the heat exchangers, so that we don't get condensation when we blow air over the cabin heat exchanger. That's sort of the tricky part. We want to provide more cooling to the experiments, but not more cooling to the cabin heat exchanger.
Hi, it's Chris Kreidler again. How are things going with data transmission from the shuttle? Are you having to do any workarounds, or is everything working smoothly now?
We're essentially in the same configuration we were in last Friday. We get the data to the ground. We do have a problem that we haven't been able to overcome with a periodic crash of the system that's processing some of the SpaceHab data. We know pretty much when to expect it and can anticipate it, and we've taken some precautions to minimize the effects of it, but we haven't been able to keep it from happening. We do, however, have the capability to record all of the data, and nobody's actually losing data as a result of these. We're able to recover all of the data. It's largely an inconvenience at this point, but it isn't costing us any science.
And last question from me. We found out yesterday that Dave Brown managed to capture a lightning elf from space, and I wondered if there had been any other gee whiz moments like that, or what's the crew's mood right now regarding the science?
I think the crew are very happy. Kelly Beck actually spoke with the crew directly yesterday, and the lead flight director. They all seem to be very happy with the conduct of the science, with the interaction between the crew and the ground. The capturing of the first ELF from space, and we were joking in the control center, was kind of a big thing. I'm not aware of any other really major firsts so far in that regard. Perhaps our scientists have had some aha moments that they'd like to tell us about, but that's the only one I think most of us are really aware of in the flight control team right now.
Marcia Dunn, Associated Press. One last question for you, Phil. Are you aware of any condensate that did form back in the SpaceHab as the temperatures rose?
No, as I said, the first failure that we had, rotary separator number 1, was due to flooding, and when we got into the floorboards, we mopped up an estimated 2 quarts of water in that incident before we switched to rotary separator 2. When we had the second problem, it was theorized that it might have been due to some amount of water. We don't see any water. And as a result of part of our reconfiguration, we wanted to make sure we weren't getting additional water under those floorboards. So we did do an inspection. I'm going to say it was about 12 hours ago right now. I don't have the exact time. But the crew reported only just a few drops of water. It's hard to say whether that's new condensation or water that's migrated out of locations from the first flooding incident. But we don't believe we're accumulating any significant amount of water under the floor now. And the crew is going in and doing periodic checks and wiping up anything with a towel that they do see.
All right, that's all the questions down at the Cape. Back here for follow-ups, Mark.
Yes, Mark Carreau from the Houston Chronicle. I had a couple questions. The first one was for Phil Engeloff, just to kind of see if I follow the strategy here. Is the kind of the strategy with the cooling system to keep the instruments warm so you can do all the science and let the cabin temperature rise a little bit if it needs to, or is it the strategy that you think you can manage both so that it doesn't get too warm or too cold somewhere?
We think we can manage both. Right now, as I say, we're in a comfortable configuration from a cabin temperature and crew comfort level. We think there's a possibility that we could actually improve that just a little bit by lowering the temperature of the water in the loop. And the trick there is to not make the water so cold that you get condensation. And we think we've got a few degrees of temperature margin to play with between the dew point of the air and the temperature of that loop. But as I say, for the moment, we're comfortable in that category. The problem is that part of that water also goes out and cools the experiment, and that's where we have sort of a shortage right now of cooling to be able to run all of the experiments that we want to at one time. So the real strategy here is to try to increase the cooling to the experiments without increasing the cooling of the cabin air to the point where we run into a condensation problem.
Okay, thank you. And I had a question for Dr. Faith. I know you've done these experiments in the past on shuttle missions and so forth. Does the industry, the automobile industry, in a larger sense, the heating and cooling people, does any of this get passed to them so that they can actually look for improvements in either the production or the operation of their equipment? I'm just sort of wondering what kind of success you've had at sort of handing off the findings you've made and are making to improve this combustion process and lower the soot production.
I'm in aerospace engineering department. My contacts in the industry tend to be in those fields. And actually, we are in pretty good conversation with the aircraft engine manufacturers in the U.S., which have some really taxing particulate emission requirements that are coming up. I think what's been done is that the work that we've done have really helped to explain to them how certain things done empirically as engineers modify things have improved soot. And I think now with this the new insights that they have, at least that's what they tell me, they feel that they can kind of manipulate the system in a more reliable way to further reduce those soot properties. I think the other one that most of us know about, of course, is the diesel engine industry, and since I'm at the University of Michigan, we also tend to be relatively close to various engine manufacturers in that area. And certain findings that some of the findings that we've made also begins to tell you how you want to carry out atomization in a diesel engine or in another liquid fuel burning engine to minimize the formation of particulates. And actually, similar tricks hold to a certain extent in conventional spark ignition automotive engines that burn gasoline. I think the insights that we're getting is that you can manipulate the mixing patterns, and that one example I tried to give you, in such a way that you can take a flame that would be brilliant yellow, burned the conventional way, and turn it from brilliant yellow to blue. An example of how that methodology can affect the practical device, those of you that are my age anyway, can probably remember that early aircraft engines like the Boeing 707 were tremendous soot producers. You could almost walk on those plumes as the plane took off. And then really NASA research or development work during the 70s came up with modified ways of injection of the fuel that have resulted in the kinds of exhaust plumes we have today, which have very little soot in them. I think the things that we're finding out by using these space flames, if you will, now have really provided the understanding of why that system works, and hopefully knowing why that system works, we can make further improvements in the future.
What kind of fuel do you use for the space experiments, and is that representative still of the kind of fuels that are burned terrestrially? I mean, is there a worthy translation, I guess what I'm asking, between what you're using as a fuel in space and what you use as a fuel on the ground?
Well, aircraft fuels that are typically used contain the fuels that we use as components of them. One that's very familiar, let's say, to farm families in the U.S. would be propane, which is widely used as a liquefied gas for heating in those applications. The other one is a fuel called ethylene, And ethylene tends to simulate some of the bad actors in practical fuels, things that really produce the bulk of the soot that you encounter in a practical application. For the experiments that we have in space, it really is for accurate metering purposes in a main spacecraft or safety for the astronauts, we really need to deal with gaseous fuels. So that's why we pick on those two. But they are representative, I think, of fuels in general, and we don't certainly our ground-based work has indicated that fuel type has a relatively small effect on these main trends that the experiments I tried to describe earlier have given us.
Okay, I think that's all the questions for today. Some programming notes before we close. An English translated replay of the Israeli VIP event earlier today involving Ilan Ramon, his Red Team crewmates, and Israeli Prime Minister Ariel Sharon will be broadcast on NASA TV at the top of the hour at 1 p.m. Central Time, 2 p.m. Eastern Time. Our daily update on events aboard the International Space Station will air on NASA TV right after that at 1:30 p.m. Central Time, 2:30 Eastern Time. All of the highlights of today's events aboard Columbia will be included in our Flight Day Highlights package, which will be broadcast for the first time at 10 p.m. Central Time tonight, 11 p.m. Eastern Time. For all of the latest information on the STS-107 mission, the Space Shuttle program, and the International Space Station, please visit our human spaceflight website at spaceflight.nasa.gov. With that, we'll return to mission control and coverage of Columbia's flight. Thanks very much.